Option Greek, gamma. Gamma is defined as a change in delta in response to the change in the spot price. But that's too technical. A better way to remember gamma is that it represents the curvature in the option price. And therefore, the more curved that the option price is, the higher the gamma. And here's the framework. Let's start off by analyzing the long call position. Now, from our previous module, we saw how we get the payoff profile for a call. So this includes the intrinsic value and time value of the call option. Now, delta is the slope at a point on the price curve. So if we pick here, the dashed blue line represents delta at that point. And if we pick that point over here, delta is represented by that tangent line. Because again, the delta is the slope of the option price curve. But you can see that the delta, or the slope here, is not the same as the slope over here. And that's what we mean by delta is changing as the spot price changes. And you can see with the call option that delta is increasing as the spot price increases. So we start off with delta over there, and then as the price keeps getting higher, you can see that the slope, and therefore delta, is getting steeper and steeper. And this is what we mean by gamma represents the rate of change in delta. So we started off with low delta here, then it started increasing, and over here the delta is becoming really high. And it's the same exercise with the long put position. Again, delta is represented by the slope at a point. So if you look at the slope here, delta is pretty steep. But then as the spot price keeps increasing, you can see that delta actually decreases as the spot price increases. And again, gamma represents the rate of change in delta as the spot price changes. Now note, for both calls and puts, the gamma is positive. And where's this observation coming from? Well, let's look at the call option. And what I want to compare is the actual price of the call relative to the delta estimate, which is represented by these dashed blue lines. You can see that along the entire spectrum, the red line is always above the delta estimate. And that's the property of positive gamma. And same thing with the put option. So you could see that the red line, which represents the actual price of the put option, is always above these delta estimates, which are represented by the dashed blue lines. And there it is. So because of the curvature, and that's what gamma is, it's curvature. So when we say there's positive gamma, we mean there's positive curvature. The option price, which is represented by the red line, will always lie above the linear or delta estimate. So therefore, delta will always underestimate the new option price in response to change in the spot price. And we can do a demonstration right here. I want you to see it for yourself. Suppose that we start off over here, right? And suppose that the spot price increases. So if the spot price was to go from S0 to S1, you could see that according to delta, the new price would be here. But if you look at the actual price, it's above it. And that's the power of positive gamma. Now, I have the urge to say convexity because the two are the exact same thing. Convexity is to bond curvature as gamma is to option curvature, but they're both curvatures. So having positive gamma is the same thing as having positive convexity. The actual price will always be better than its linear estimate. And this is also true for the call option. So if we started from here, and let's just say we go from S0 to S1, once again, according to delta, the new price would be there, but the actual price would be on the red line. And you can see that the red line is above the delta estimate. So what are the implications of positive gamma? This would mean that option price will increase at a faster rate. And let's have a look at our call option as well. So you can see for an equal increase in spot price, so if spot price is increasing, you can see that the value of the call option is actually increasing at an increasing rate. On the other hand, if the spot price is decreasing, you could see that the value of the call option will decrease at a decreasing rate. So if the spot price is decreasing, you could see that the downward trajectory is starting to flatten out. That means the descent is getting slower and slower. And it's the same thing with the put option. You could see that as the value of the put option decreases, it's sort of flatlining. So the rate of descent is slowing down. So if we're going this way. On the other hand, if we're going this way, in which case the put option value is increasing, you could see that it's increasing at an increasing rate. So with positive gamma, there's two ways to look at it, and they both say the same thing. We can say that the new price will always be higher than the delta estimate, but that's also in line with saying that when the price changes, in other words, when the price increases, it increases at an increasing rate, and then when it decreases at a decelerated rate. Those two would lead to the same result. In other words, the actual price of the option will always be greater than its linear estimate. Now gamma, again, remember gamma is curvature. So gamma is highest, i.e. option price is most curved, when it's at the money. That's when the spot price is equal to the strike price. First of all, let's go have a look at our visual framework. And here it is. You could see over here it's flatlining, and over here it's sort of, again, it's just going on a linear trajectory. Here it's going at a linear trajectory towards 0. Here it's going towards a linear trajectory towards 1. So therefore, the options would be most curved right in the middle, and that's when the options are at the money. Now, what's the logical explanation as to why gamma is highest when the options are at the money? Because at that point, the option is literally sitting on the fence between going in the money, in which case the delta would be converging towards 1, or out of the money, in which case delta would be converging towards 0. In other words, when the option is at the money, it's really at a turning point, and therefore the rate of change in delta will be very high. So here's another visual depiction. So this is a call option. So you could see when the option is at the money and you're looking at either side of the fence, it can either go towards delta 1, or on this side it could go towards delta is equal to 0. So naturally it's going to be most bent or most curved at that point in time. And we have to remind ourselves that gamma is the rate of change in delta. So, you know, if we're going from let's say this point to that point, delta is not going to change much because it's going to go from, let's say, 0.9 to 1.0. But if you're sitting on the fence, on one side it could go towards 1, and on the other side it could go towards 0, then it's really at a crossroads. So the rate of change in delta will be very extreme at this point. And it's a similar story with a put option. You can see if we go this way, delta is converging towards -1. If we go this way, delta is converging towards 0. And again, if we're going from this point to that point, maybe it'll go from -9 delta to -1 delta. That's not a big change. But if you're sitting here, on one side it's going to converge towards -1, and on the other side it's going to converge towards 0. So delta is very susceptible to change at that point in time. So therefore, the higher the gamma, the more unstable the delta will be. And again, when is gamma highest? When the option is at the money. So when it's at the money, gamma is high, delta is very unstable. When it's deep in the money or out of the money, gamma is low, and therefore delta is more stable, as I demonstrated before. Let's just look at the case of the put option again. If I'm going from this point here, maybe it's going from -0.9 to -1. That's not a big change in delta. Similarly here, if I'm going from there to there, maybe this is going from -0.7. I'm sorry, with a call option, delta is always positive. So from here it's going from 0.7 to 0.8. That's not a big deal. But when you're at the money, then delta can change dramatically. It can either be converging towards 1 or it could be converging towards 0. So therefore delta becomes very unreliable. Why am I making such a big deal about delta becoming unreliable? Because later on, we're going to see a lot of hedging strategies that are built upon delta. So if delta is not stable, how can you have a hedging strategy that's built on delta? So that's the issue. Note 4, assuming that the option stays at the money, as the option approaches expiry, gamma will simply increase even more. And here's a visual depiction of what's going on. Let's start off with the red line. Red line is 10 days before expiry. Now, what's the difference between the option price and its intrinsic value? The option price also contains time value. That's the potential for an even higher payoff before expiry. Yeah, but as the expiry date approaches and that window of opportunity shrinks, the potential for higher payoff becomes less and less and less. And that's why you see that the price curves are converging towards their intrinsic value. So with only 2 days left to expiry, we get the green line, which is actually, like I said, converging even closer to intrinsic value. And then finally on an expiry date, there is no more time value. So all you have is intrinsic value. But we're here to discuss gamma. And look what's happening to curvature when the option is at the money and we are approaching expiry at the same time. Because the curves are moving in, they're getting more bent. Why are they getting more bent? Well, first, why don't we start off with the two extremes? We know that on this end, delta is 0. We know at this end, delta is 1. That's not going to change. That's not going to change. You could see that going from the red line to the green line to the black line, delta is pretty close to 0 here. And similarly, at this end, when the option is very deep in the money, delta, all these deltas at that price are very close to 1. But over here, you can see that it's actually moving inwards. So the wings are fixed, but the body here is moving in, which means it's becoming more bent when the option is at the money. In other words, it's becoming more curved, and that's exactly what gamma captures, is curvature. So there it is. As the option approaches its expiry, and assuming that the option is trading at the money, its gamma will become higher and higher. In other words, it's becoming more and more curved at that point. Now for the underlying asset or the forward on the underlying asset, there's no curvature because there's a one-to-one relationship. So if you're looking at the spot price relative to the spot price, it's always a one-to-one relationship. There is no curvature. So therefore, there is no gamma. In other words, change in spot or change in forward is always linear. As we said, there is no curvature.